Hello everyone, we are back again. Hope you're keeping safe and well in this time of pandemic. In this video, we will discuss Hawking radiation, the true way to explain it. If you've heard about Hawking radiation, you probably have heard the following explanation. Particle and antiparticle pairs come out of nothing. When one of these pairs happens at the edge of the black hole, one of the particles falls into the black hole while the other is able to get out. However, for the second particle to get out, it needs energy. And the only thing around is the black hole. And because of that, it just goes away faster and faster. And energy is equal to mass, as discussed in the last video, so the black hole shrinks and eventually disappears. Except that leads to a lot of questions, like shouldn't the particle coming into the black hole be giving mass to the black hole? So I am going to tell the true way Hawking radiation works. So first, we need to understand two things: black holes and quantum fields. Black holes form when a very massive star dies. For example, assume that this is a massive star for a moment. When it dies, it will result in a supernova while the core collapses in on itself. And here, one of two things can happen. One thing that can happen is that the core is not massive enough to become a black hole, in which case it becomes a neutron star. But in the other case, it becomes a black hole. A black hole. Yeah, so it becomes a black hole. So, in that case, what are black holes? Well, black holes are when a bunch of matter is compressed into such a tiny space that not even light can get out. This radius is called the Schwarzschild radius. And actually, for the Earth to become a black hole, it would need to be 1 centimeter wide. The sun would have to be a few kilometers wide. Only the biggest stars are able to become a black hole. Most of the time, it is just white dwarfs, and even in the time that stars are massive enough to avoid white dwarfs, many of them become neutron stars as well. So black holes are, at least the stellar types, though the most common types of black holes, they aren't really too common. And as I said, nothing can come out of it, even light. If you go away from the black hole, you won't be simply pulled in. In fact, you might be able to get out, but any path you take will lead you closer to the black hole. And thus that makes the way to survive the longest in a black hole, while in a black hole, is to do nothing. And just do nothing, don't move, or because even if you move the slightest bit outside the black hole, it's going to make that path curve toward the singularity. And since light can't escape them, they are given the name of black holes. Now, quantum fields. Now first, let us imagine that there's a box, and in that box there is a particle. Okay, wait, why isn't this box? Yeah, in this box there is a sort of particle. I by mistake drew it as a line, but please take into account that it really is a point particle. And we normally like to imagine as it is being a simple point and it's moving all around, and this is the path of the particle. However, in reality, according to quantum theory, which is the most accurate theory we have, actually, this isn't true. Instead, the box is filled with a state of probabilities for where that particle can be. almost all those probabilities are hovering near the 0 mark. It does not mean that a particle cannot be there, but it does mean that a particle is very unlikely to be there. An electron can be right in my nostril right now. But though it came from an atom on the other side of the universe, yes, that is possible. So, because of this, there are a bunch of possibilities or probabilities, which I'm dotting in red. And when one of those probabilities is not 0, it's closer to 1, then that is a close approximation for the position of the particle. So in reality, it's kind of a probability. Now, in a vacuum, there are a bunch of positive and negative waves around. Like I'm drawing some positive waves with my red marker and negative waves with my blue marker. Yeah. However, usually there's a balance between them, and in that case, it is a vacuum. This is what most people mean when they talk about virtual particles. However, when a real particle is there, if it has a positive, if it is a normal particle, then the positive probability is very high, higher than the normal particle, and that is enough to make the normal part, that part of the particle real, in which case it becomes a real particle. Meanwhile, assuming that there was a negative particle here, well then the negative particle will create more negative probability waves than the positive probability particle, and thus there will be a negative particle. So normally these are in a balance. However, now I'm going to take an analogy. This will help later on. Okay? Now let us say that we have two blocks, and there is a string between them. Okay? Now let us say you strike it somewhere, say in the middle, then it's going to wave at a certain frequency. In fact, it can wave at a bunch of frequencies. However, the one which are the most simple are actually the easiest one. These are the most dominant. The ones with the fewest loops, however, are the ones that happen the most. For example, there's the 1 loop situation, the 2 loop situation, the 3 loop situation, and so on. They are just waving. Now, imagine what happens when you pinch this point in place and then strike it. Well, in that case, that point, it's obvious that it can no longer wave. So, the other part of the string can move, but that part can't move. And some of the possibilities for it have been locked out. And this is kind of what the black hole does. Before the black hole, the particles are in a vacuum. However, when the black hole forms, this black hole kind of pinches these waves of probability. And all of a sudden, because of the black hole around it, it is filled with particles. However, don't think that these happen just at the event horizon. They happen from the event horizon to a radius a few times the event horizon. And trust me, it is way easier for these particles to escape from here than here. So there's only one thing. However, still, they need energy. And the only thing around is this black hole. Now, actually, Hawking radiation at the beginning is almost exclusively photons, particles of light. And I'm not talking about the normal visible light photons, or even the microwaves you use in your, microwave. These are extreme radio waves. By the time they come out of the black hole, their radius is like at least 80 times the width of the black hole. And let us say that this might be what the wavelength looks like, an approximation. This might be the smallest it can be actually. And this is not to scale, this is a tiny black hole. So, as I was saying, By the time it reaches you, it's an extreme radio wave. However, nonetheless, it needs energy, and the only thing around is that black hole. Eventually, however, it will get smaller and smaller, and if it gets smaller, then it kind of pinches it harder. This makes more states unavailable, which means that even more particles come, which lead to even more particles going out, which means a faster evaporation. At the very end of a black hole's life, it will be ejecting so much energy that it will start producing real particles, not just normal photons, but real particles like electrons and photons and neutrons and later even muons. And eventually, in its final moments, it will be ejecting all the mass it has, and it will explode with a gigantic boom. So that's the process. First, a particle is really a bunch of probabilities, and normally a vacuum is a combination of positive and negative probabilities. This point, it is useful to imagine this analogy where there's a string between two blocks. The string represents the probability. Normally, it has access to many different vibrations. For example, this. However, if we pinch the middle of the string, then all of a sudden, these two modes and a bunch of other modes of vibration are all of a sudden unavailable. The black hole does a similar thing with space-time, pinching it, and thus because of that, all of a sudden there are a bunch of particles around, and because of that, these particles escape. And since there is only one thing around, the black hole, the black hole starts shrinking, and yeah. However, to clarify, this is still not even starting to happen with all the black holes we have around, unless there's some primordial black holes floating around. Those are ones that were formed at the very beginning of the universe, and they are at most a centimeter wide. Often they can be even atomic size, and they will, despite being the mass of like Mount Everest. Yes, that is true. The mass of Mount Everest in the size of an atom. That can happen with these primordial black holes. So because of that, that's the smallest. However, unless that is the case, every black hole is shrinking so slowly that whatever they eat still makes them grow, and grow a lot. Even isolated ones which have calmed down and aren't eating anything are feeding on the cosmic microwave background, which is basically the thing that happened that is close to the very edge of what we can see. It's basically a bunch of microwaves these are light waves that have traveled since the beginning of time, almost 380,000 years after the beginning of our universe, when the universe is 13.8 billion years old. However, the isolated ones still are feeding on them, and that makes them grow. Don't forget, these waves are extreme radio waves. Microwaves are a lot more powerful than radio waves. In fact, they can be harmful, though infrared isn't. So, because of that, no black hole at this time has even started beginning to shrink. Like, no black hole, sorry, it is blue, but black holes are not blue. Yeah, no black hole has started shrinking yet, because Hawking radiation is such a slow process that most black holes are just growing, either feeding on like stars, either they're feeding on stars, like they're feeding on that, or they're feeding on the cosmic microwave background, which is full of microwaves. Microwaves, not these radio waves. So right now, no black holes have started evaporating, but in the far future, once the once all the stars have gone and once the cosmic microwave background has just gotten undetectable, then the black holes will start evaporating. However, it will take a long time for all of them to evaporate. A black hole with the mass of the sun will take octodecillion years, more than that actually. It will take, well, a number which is a 1 followed by 67 zeros. And the largest black holes, which are billions of times the mass of our sun, will easily last for millions of googles of years, which is a 1 followed by 106 zeros. So no black hole is, so it's going to take a long time for black holes to evaporate. Anyways, that's what I wanted to say. Thank you. Bye bye.